And the next computational method we'll consider is agent-based models. So the idea here is that you have these entities, agents, which obey simple rules, but you have lots of them and you put them in a computer simulation and you allow them to interact, and you get emergent behaviour, things that aren't necessarily in the rules themselves but are consequences of the rules. And then the idea is that if that emergent behaviour matches what you actually see in history and society, then the rules being followed by your agents presumably capture the rules that operate in history and society and that underlie the patterns that we see. And an early example of this was the work of Thomas Schelling. Now, he was working in the mid-20th century. He didn't have computers available, so he used very simple models. One of the examples was a model of neighbourhood segregation. Neighbourhood segregation. So he was interested in the way, neighbourhoods separate into different ethnicities or different religious affiliations or what have you. And what he showed was that neighbourhood segregation can occur even when individually people aren't that bothered about it. But if they have even a slight preference to live with their own kind, then neighbourhood segregation emerges and you get clear blocks. And how he did this was with a chessboard. He took a chessboard and he put coins on it. So he says pennies and dimes he used to represent the two ethnicities or nationalities or what have you. You could also have, heads and tails. So a given person is surrounded by up to 8 neighbours, and he said that let's have that people prefer to live with a third of their neighbours are the same as themselves. And he I think used 45. He filled in 45, or he had 45 coins, one of each type, and so 45 coins, or maybe it was an even number, but 45 coins, some heads, some tails. So that on a 64 square chessboard, that leaves some spaces free, and at each move, anybody who is not surrounded by at least a third of their neighbours being of the same kind can move to a blank square, an empty square. And he showed that if you keep applying that rule, then you get blocks of all heads here, all tails there, that these segregation occurs. Even though you'd think, well, people aren't that prejudiced, they're only asking for a third, not even a half. But nevertheless, with that, segregation occurs. So from a simple rule, you can get an emergent phenomenon of neighbourhood segregation, even though the agent rule is not asking for segregation per se, merely a slight or a minimum preference for how many neighbours are of the same kind. And Schelling's work was taken forward in this book, quite an important book in the development of agent-based modelling as an approach to studying social systems, growing artificial societies by Epstein and Axtell. And their model is based on something they called sugarscape. So this is a grid like Schelling's chessboard, but with more cells to it. But you know, I haven't drawn the individual cells. And the idea is that there are these two sugar mountains. So these are cells that have a resource which they call sugar, and the density of sugar varies. So at the centre of the sugar mountains, there's a large amount of sugar. Then there's a lower density of sugar in this area surrounding it, and then a still lower density of sugar in this area. And you then have agents that can move around this grid, and the agents harvest sugar, and they also consume sugar. So they need sugar, but they can also accumulate more than they eat if they find a rich source. And they have only limited vision, so they can't see the big picture. They can just see a few cells around them, and their objective is to move towards where the sugar is densest, so that they can harvest the sugar. And then they so with that very simple rule of the sugar regenerates as it's consumed, it later regenerates. So they then observe how these agents move around, and naturally enough they tend to congregate and end up on the sugar mountains. And what they showed was that if you stop this simulation after a while and look at how much sugar each agent has, yes, you get the classical Lorentz curve showing inequality in incomes. In this case it's sugar and agents. So the agents with the least sugar have far less than their fair share, and then there are some agents with a lot of sugar who have far more than their fair share. You saw the Lorentz curve in a previous lesson. So with this simple model, you generate that income inequality that is found in society, suggesting that this may capture some dynamics of that. Now, I didn't explain all the rules. There's also mating in this basic model. So these agents are of two different kinds, and they can mate and endow their offspring. And you can elaborate this further with trade. So they then sort of extend it that there's two types of resource, sugar and spice, and agents can have one or the other, and then they can trade. You know, they trade with each other because they need both. And you can have war. You know, they plunder each other, and so you can make the rules more and more elaborate and reproduce the socio-historical processes that we see in real society. At least that's the idea behind this. And so we can, if we can do that, we can suggest that the rules applied to each of these things are those that are operating in the real world. That's the objective of it. And they call this, has been called this agent-based approach with these rules, generative social science. So instead of sitting in your study, scratching your head and thinking about how societies work and writing it down, they suggest you go down to the computer and you come up with your rules and you play around until you can produce the patterns you see in society. And then, you know, it's not arguable. You've actually generated that behaviour and shown that your rules must be the ones that apply. related to that is the idea of cellular automata. Now, in the Sugarscape example, the agents can move around as they could in Schelling's chessboard neighbourhood segregation model. They could move to empty squares. With cellular automata, you have a grid of cells, and what happens in a particular cell, it updates depending on its neighbours. So an example is the game of life. Developed by the mathematician John Conway, which has the rules that each cell is either black or white. And black means alive. Well, perhaps I should have just said each cell is alive or dead. What colour you use is up to you, but usually would be used black or white. So it's either alive or dead, let me say. And if 2 or 3 neighbours are alive, the cell can stay alive if it's alive already. And if it's got exactly 3 neighbours, then if it's dead, it becomes alive. And in any other condition, the cell dies. So either dies because of overcrowding, too many neighbours, or because of loneliness, not enough neighbours. And with these very simple rules, you can get very complex behaviour. You can see on YouTube videos of elaborate games of life showing some of the incredible structures that can be produced from this. One of the simplest but amazing things you get out of this is the glider, which looks like that. It's so those cells are alive, and this is in a grid which I haven't drawn, but all the surrounding cells would be dead. And this glider, by following those rules, it transforms through 4 steps, and then it eventually ends up as the same shape again, but it has moved down by 1 square to the right and 1 square downwards. So it's moved along and down. So it kind of will move across the grid. What I haven't shown is the in-between shapes where, for example, one of them looks like that. So see, I think that's the first shape after this one. So it kind of does that, and then it does a few other things, but it then ends up like that. So with every 4 steps, it looks the same, and it just glides across the grid. Now, that's not particularly useful for studying socio-historical processes, but the same idea can be used for studying socio-historical processes. So one person who's used cellular automata to study socio-historical processes is James Bennett, who's modelled the development of empires across Eurasia using cellular automata. So in each cell you've got elites and peasants who can increase in their numbers, and if the society is doing well, the elites tend to increase more quickly, and then that can lead to the society or the cell gets more prosperous. It can attack neighbours, and defeat them and build empires. As the empires grow, the elites grow. So let's say forming empires. And then the elites can start to squabble among themselves, and the elites split as a result of a kind of civil war. If you've got top-heavy numbers of elites, they squabble, they then will split the empire. So that will spawn daughter empires, which can then repeat the process and start conquering their neighbours. And in this way he shows that you get a pattern of empires growing and contracting and splitting across Eurasia, that the statistics of those empires are the same as the real statistics of the real empires through history. So for example, if you look at a particular cell and ask how often was that cell, and here you're talking about a particular cell, a particular part of India, let's say, and ask how often was that cell part of an empire, then it corresponds to how often that cell was part of an empire in real history, suggesting, so I should say as well, he's taken into account the different topography, the deserts and the fertile areas and where there's ocean and so on. So suggesting that the geography of Eurasia and this dynamics that he's come up with here explains a large part of the dynamics of imperialism across Eurasia for the last few thousand years. Quite an achievement. And it's I think he would say something like it explains 60%, or I'm not sure exactly what the figure is offhand, but so I said it matches the real statistics. Well, it matches it to a certain extent, something like 60%. So it explains a certain and a large amount of the real history. And that's all done with a cellular automaton. Nothing's moving around. It's just each cell affects its neighbour. It can absorb it into an empire or split off from it. And then another example is the tribute model of Robert Axelrod. So here he imagines a set of societies arranged around a circle. So there are 10 of them, and each society has a certain amount of wealth, which equals power. And at each go, 3 societies are chosen and they have the option to attack a neighbour. Well, attack, demand tribute, firstly, from one or other of their 2 neighbours, and they choose the one that is weakest, i.e. has less wealth. And the one that is the weaker can decide whether it just pays up or it chooses to fight. And if it fights, they both lose a certain amount of their wealth. They lose wealth in proportion to the wealth of the other one. So the stronger, wealthier one comes out better because it loses an amount proportional to the wealth of the weaker one, whereas the weaker one loses an amount proportional to the wealth of the stronger one, suggesting that a wealthier, more powerful one can inflict more damage on a weaker one than the weaker one can inflict on the stronger. But then the real point of this model is to create or study the dynamics of alliances or coalitions. Each society has, or societies can have loyalty or commitment to their neighbours. Let's say commitment. Depending on if they pay tribute, then they're considered to be on the same side, or if they have fought together on the same side, then they become more likely to fight together in future. And if they've fought against each other, then that reduces their commitment. So that when a society decides to attack one of the other societies, it can recruit its alliance, its coalition, those that have paid it tribute in the past or fought together with it in the past. So that makes it even stronger, and they're more likely to win. And then so it's even wealthier, and so it's more likely to be able to force others to pay tribute. So not only will that make it wealthier, but it will also get it allies. And what Axelrod shows then is if you study through time a particular society, you find that its that should be wealth up there. Its wealth tends to increase through these rules, but it eventually gets into a configuration where everything unravels and the wealth suddenly collapses. And he suggests that this is, a good model of how empires form in history, that they're attacking their neighbours and everything seems to be going well, but then they overstretch themselves and the whole thing collapses. And if you do this for all 10 of your societies on a particular go, so that's society 1, 2, 3, 4, etc. You'll find that some of them do this, some reach greater levels of power than others, and some of them don't really rise at all. So again, he suggests that this is like in real societies, that some of them come to dominate and others are dominated. Now, before we move on, there's a couple of other points to make about agent-based modelling. Firstly, it's been criticised for ignoring the structure agency debate. So with agent-based modelling, the clue is in the name. It's all about agency. So the little agents, obeying their micro rules, generate emergent patterns, so they generate social structure. But sociologists and theoretical historians have long realised that social structure constrains what individuals can do. And this closing of the loop of structure back onto agency has tended to be neglected in agent-based modelling. And it doesn't have to be that way, though. The work of Jim Bennett on the ebb and flow of empires across Eurasia involves the idea that the behaviour of the individual cells in his model is affected by whether they are part of an empire or not. So in that case, the emergent structural phenomenon of empire does affect the behavior, the agency of the individual cells. So it's possible to imagine how structure could be incorporated into these models, even though historically it is something that has been de-emphasized. And the second point to mention is that there's something called NetLogo, which is a computer program for creating and running agent-based models and other kinds of models as well. And it's free to use. Just Google it and you'll find the website. You can either run it online or download it to your computer. And it comes with a whole set of existing models, including, for example, the Sugarscape model that I mentioned, so that if you're interested in playing around with these computational approaches and even developing your own, then NetLogo is a very good way to do that. It's simple to use and it's free to use.